Hello, my name is Jakapat Petnin. Today I want to present cooperative education in topic Impulse Radar Imaging System. Supervisor is Assistant Professor Dr. Kisada Mama. I conduct this project at the Department of Electrical Engineering, National Chung Cheng University. This is our operational details. As I work, first study the articles Impulse Radar Imaging System. Check the cost millimeter wave, RF integration, circuit design and energy harvesting. Support the first and second year master degree students in the Electrical Engineering Department in researching Impulse Radar Imaging System. Compare the techniques of creating image using microwaves between the methods of back projections and fast back projections. Problem and obstacles encountered during the work. Participating in class that are explained in Chinese. Communicating with college or explaining words may be hindered by technical terms that cannot be immediately understood. Using the MATLAB program because the operator has little experience using the MATLAB. Writing the Verilog language, which is a coding the operators has never used before. Benefits that are received from the first experience. Communication skills and coordination with the other people. The decision to study for a master. Responsibilities for assigned tasks to college and teachers. Solving problems from actual work. Training in MATLAB programming skills. Understanding Impulse Radar from studying actual. This overview of research describes the use of special physical properties of Impulse Radar to imaging humans behind the wall by antenna that is a bistatic. It uses different sets of transmitting and receiving antennas. Then use microwave imaging to process signal to obtain images of humans. The works will be divided into 6 parts. Hardware for 4 parts. Transmitter, antenna, Impulse Radar signal through the wall, receiver, and the software 2 parts. Data managing and imaging can specify the locus of human. This slide shows about the transmitter part. First, we generate a pulse signal that's measured at a rate of 5 million times per second or 5 MHz. This pulse signal is then divided and monitored using an oscilloscope for tracking the signal's behavior. Next, we generate a carrier signal with a frequency of 4.5 GHz, which will serve as the carrier wave. This carrier signal is then amplified to provide sufficient power for use with a mixer. The pulse signals from the pulse generator is mixed with the carrier signals from the voltage control oscillator or VCO. And after mixing the signals with amplified gain to ensure it has enough power for transmission. Finally, a filter is used for suppress any unwanted signals, ensuring that only the desired signal is broadcast. This slide shows about the generate impulse signal with a width of 200 picoseconds. In Figure 3, SRD diode has feature to release stored energies in a short period of time. Figure 4, after the signal has passed the SSR diode, The signal is transmitted in two ways, through the main line and through the stub. By the stub, determine the pulse width in figure 5. Depend on the adjustments of the variable LD when the signal reflects at the short end, the signal reverse phase by 180 degrees. And the figure 5, wave 1 catched by the reverse bias current accumulating and releasing energies, and wave 2 catched by a reflex at the short stub. Then the lessons why the reflex wave has a faster speed than the main wave depend on 2 times the length of stub tunings less than the length of main line. Finally, wave 1 and wave 2 will cancel as other out, resulting in an impulse signal. From the previous slide, use the signal to create impulse, but the signals obtained from the electrical circuit has an asymmetric signal. It makes it difficult to troubleshoot electrical circuits on PCB. FPGAs can creating digital circuits by hardware programming, which is easier to fix the circuit in the PCB method. In the figure 6, impulse signal can know the distance from the time delay between the transmitters and the objects, and it has the ability to through the world, providing precise and accurate imaging from its scattered bandwidth in frequency domain. In figure 7, CW or continuous wave signals cannot know distance and speed, but it's using a Doppler radar. It has a different frequency as the objects move closer to or any from the transmitter, giving it a different speed of objects. This is the advantage of impulse radar. According to FCC standard in the UWD or ultra wideband frequency range of 3.1 to 10 to 6 GHz. The EIRP is 41.3 dBm. Due to the energies of the wave speed expressed over a wide frequency range, it is less affected by noise and has high resolution, allowing it to separate objects that are close together well. It can detect small changes accurately. Next, we talk about the antenna. Figure 8 is the monopole antenna. It works in the 3 to 6 GHz frequency band. It is an omnidirectional pattern, so it has a great impact on the multipath threading. It uses a transmitting and receiving antenna. It can specify the locations of the object in only 2 dimensions. And the figure 9 is Vivaldi antenna. It works in the 3 to 6 GHz frequency band too. If you use it for visual array MIMO, it can increase aperture, so it can do beam steering for scanning the height of humans in 3 dimensions for high accuracy, and then reduce noise from multipath threadings because it is the directional pattern. And use LabVIEW is a graphics program that can be designed to control hardware by programming. First, LabVIEW controls Arduino is used to change the phase by switching the transmitting antenna for control beam of antenna. Phase adjustments make the radar scan images of humans. So this is a concept of phase array using phase shifter to control the phase of the signal in an antenna array consisting of one antenna connects to 4 Vivaldi antenna elements. From delta t is waveform propagation time by diagonal matrix relationship between d, l, and zeta variable. There is a phase shift relates the distance and wavelength, so the delay time is converted to a phase delay volume. When the signals coming out from S antennas is delayed in phase, the waveform is obtained as shown in the dot line. So this case is a test case. Define the distance of Vivaldi is 4.6 centimeters. Center frequency is 5 gigahertz. And once the angles of beam steering is 30 degree. And one to phase change is 2.40x radians. So figures 11 clearly show why this system want to change the beam formings, showing a schematic of the antenna scanning the human high target length. And lab view control the program power supplied by controlling the switch to change the receiving direction with the voltage that determined which receiving antenna is used to receive the signal. Finally, lab views also have in display the result. It is responsible for receiving and processing signals. The main job of oscilloscope is receive signal from the receiving antenna and convert these signals into data in an Excel format to efficacious data storage and analysis. And this slide talk about the Fish equation. Fish equations is used to calculate the received signal power when the signal is transmitted in the free space. Step 1. The energy emitted from the radar transmitting antenna. This distribution represents the distribution of the transmit energies on a circular surface, showing the energy density decreasing with distance. Step 2. The gains added to the equation represent the intensities of energy radiated from the antenna in a given direction. Step 3. When the power of the reflex signals hit the target, the equations for the cross-section areas of targets and the energy leaving the targets are formed. This distribution represents the transmitted energies on a circular surface, showing the energy decision decreasing with distance. Step 4. When the signals arrive, the receiving antenna gain value is related to the antenna area and the wavelength of the signal radiating from the antenna. This slide talks about the impulse signal to the wall. Figure 12 is a reflection of a state of impulse signal without signals angle reflections to wall. When the incident signal hit the wall, the signal power is attenuated with a reflection index. Follow figure 13. The power transmitted across the first interface into the medium is attenuated with transmission coefficient. Follow figure 14. The secondary reflection is attenuated with reflection index multiplied by transmission coefficient. Finally, the power available to create the wall is attenuated with the power to with transmission coefficient. And it is a part of the receiver part. First, the receiver receives the signal from the antenna, which typically come in the weak and volatile. These signals are then amplified to a more usable level. Next, the signals is divided in preparation to be mixed with the in-phase and quadrature signal. The IQ signals processing then reduce the signal frequency to range that can be easily processed. After this, the signal received from the antenna is combined with the in-phase and quadrature signal to bring the signal to the baseband. Finally, a low-pass filter is applied to the signal to obtain a smooth radar image while also removing any high-frequency components that are not needed. So in-phase and quadrature signals. Why do systems need to separate the signal into the I or Q signal? If we want to directly process phase and amplitude at very high frequencies, this is a bit difficult using the mixing to bring the signal to the baseband. And it enables accurate signal directions, calculations, angle of arrivals or AOAs by calculating the phase difference between antennas. First, the signal received from the antenna is a high-frequency signal is given by function st, which need to be processed for further use. Next, a low-cut oscillator is used to modulate the signal down to baseband. After that, a complex signal is obtained for analysis, and the IQ data is used to calculate both the amplitude and phase of the signal. The next step is used to calculate the amplitude and phase from the IQ components. Finally, by examining the phase difference between the antennas, we can calculate the angles available. So this is the image is a measurement showing the positions of the human to obtain the signal functions Rn. So the n available is given by the used to the reflex signals of the n-channel antenna as a discrete time. K is the discrete domain in fast time samplings of K. L is the time domain classifications of filters of objects as a human breathing signals of fuse movements. The function Hn is the human breathing signal. The Cn is the steady signal. The Wn is the white noise signal. The Qn is the not stable signal. This is used for list data from receiver antenna. So the available sex is set to 60 to detect body movement signal because the human's body beating frequency is 15 times per minute. So it is selected to receive signal 60 times in 15 seconds. And the variable nums is numbers of data points per second. The waveform generator is set up to 5 MHz or 200 nanoseconds, and sampling rate is 25 gigasamples per second. Therefore, it had 5,000 sample points. After that, the means of the first half of the data points is the subtract from the S segment to remove any DC offset. And to obtain only human breathing signals, coupled signals and a stable signal that do not change with time and have approximately the same amplitude are considered stable signals. Therefore, use the means subtraction method to remove time invariant signals. This slide explains how to use the linear least square or LTS functions work in the MATLAB. The first equation is a linear model of degree m power minus 1 has the metric form this equation. And the equation B cannot calculate beta directly because the epsilon is unknown. The linear least square fitting method approximates beta by calculating a vector of coefficients B that minimize the SSE. Curve fitting toolbox calculate B by solving system of equations called the normal equations. The normal equations are given by this formula. To calculate the vectors of its response values y vector, substitute B in the model formula y vector. And use the LTS method to remove the linear trends. Remove linear trends to focus on more complex signal behavior. And use the Butterworth filter design functions. Butterworth filter used to design an n-order low-pass digital Butterworth filter with normalized cutoff frequency. So it depends on Nyquist frequencies of sampling rate. The Butter functions return the numerators and denominators coefficients of the filter transfer function. And next, digital filter functions filter the input data using a rational transfer function defined by Butterworth filter design. Finally, use the smooth data functions. Smooth functions used to prevent the noise and use low-pass filter to focus on the relevant low frequencies components of the signal. This slide shows the signals after use the smooth filters and low-pass filter. The purpose of the measures the variance of the data in the slow time dimension is to have identified the area of the high variance possible due to the noise. High variance indicate an unstable signal, and it have to highlight area of the signal variations, thus enabling the severance of the digital objects. The mu is the means of the YL in length of 60 samples. So this is the method for data transformations. In the orange box is used to store magnitudes of the signal direction of the signal in the positive and negative components. And the green box is used to remove the signal during the time periods of the system delays and pulse widths so that there is no potential noise or signal cluster in the period. And the red box is back to the calculate to obtain signals with both magnitude and directions after adjustment. And the method of the normalizations. Normalizations is useful to reduce the size of the space data in the dataset, making it easier to understand and analyze. So the magnitude of the data is in the length of 0 to 1, for finding the strongest signals among the 16 channels is the average of each signal. And this slide shows about the imaging algorithm. First is the back projections. Back projections is a process that reverse receive data to create an image using information relative to the position or angle of the signal being transmitted. The basic principle is to calculate how the measure data as its sensor positions should be back projected to the area where the signal likely to originate. Follow this algorithm. It is an image generation method that processes the data incrementally over a series of angles and distance, which is a pre-process before looping through the angles and distance. The algorithm calculates the distance from the origin to each pixel, compute the phase delay and propagation distance, and then integrate the phase offset from the antenna before transforming the data into a Cartesian kit. The final step involved normalizing the image and display it on a logarithm scale. So the figures show that the near-field beamforming techniques are important for accurately generate radar image when targets are in the vicinities of the detection system. The received signals as its antenna consists of an interface given by AI and the coordinator given by BI, which will create a representation of the signal in the complex form as a specified given by ZI. The beamforming process is used to generate a signal in a given direction. The resulting beamformer intensity is obtained by summing the phase offset signal from all the receiving antennas at described in YN. The received signal is received from the transmitter and is propagated to different antennas. Each antenna has a different distance. Distance from the transmitter to the antenna is determined by Rn, and the phase offset for each receiving point can be calculated as phase n. And the second method is the fast back projection. Improve computations efficiently by starting from the generations of the image kit and using a modified mapping method. Instead of processing distance and angle one by one and in back projection, it reduces the numbers of needs loop, reducing computational complexity and speeding up image generation. And the last slide we talk about the result of the research. For the back projections method, it works at the speed of approximately 782 megapixels per second, provide a high resolution. The finally is the fast back projections work at the speed of approximately 2006 megapixels per second. Suitable for real-time sensing with a small loss of resolution. This is all my work when I work at Taiwan internship. Thank you for listening.